My name is Bill. So in the past, my videos have all been about books, but I'm planning on doing videos about my programming projects from now on. The channel name was changed from Bill's Books to Chaos Continuum, but there might be some more chaos in the future. If I might have to change the channel name again, because I recently discovered that there's another channel using that name. So in this video, it's about doing the Mandelbrot Set in Python using Pygame and numpy. So in the program, you import Pygame, numpy as np, numba import JIT and complex 128. So I use a just-in-time compiler for the Mandelbrot Set to speed it up. So it compiles it before it runs it instead of using the Python interpreter. So for the data, I create a numpy array. The size of that is by the number of pixels I want in my image, and the corners are the define the rectangle in the complex plane. So I calculate the range for the real and imaginary parts, and then scale for the width and height. But then, to keep from distorting the Mandelbrot Set, I take the maximum scale and use that to scale both the X and Y. So I'm using a maximum of 100 iterations. I need to change that to a variable that I can set somewhere, but that's for a future version. So here's something interesting in Python, is you can do a double loop on one line. So it takes the shape of the matrix, so it goes through all the rows and columns of the matrix. Or I've got a simple example of that here somewhere. So create a matrix that's 3 by 4. So the data type is float 64, and if you print out the matrix, so you got 3 rows, 4 columns, and then if you print out the loop indexes, it goes through all the columns for the first row, and then the columns for the second row, and the columns for the third row. So I just recently started using Python, so this is all new to me. also there's complex numbers in Python, so you can calculate directly with complex numbers. So I take whatever value I start with in the corner and add to where I'm at in the image, and then the color defaults to the maximum iterations. So the loop count starts at 0. So my Z1 is set to this complex number here. So then this is the while loop that calculates the trajectory of the Mandelbrot set for each pixel. So it'll go until it exceeds, till the magnitude of Z1 exceeds 2. And then the color is set to the count. So the first time through, this will be 0 if it exceeds that at the beginning. You break out of the while loop, but normally you do this is the formula for the Mandelbrot set, so it's Z squared plus Z so then you just iterate that, so each time Z1 is updated, it becomes the value for the next input, and you increment the count. So do this until it exceeds, magnitude exceeds 2, or the count exceeds num. And then the color is assigned to that pixel in the array. So then, or the matrix, so then the matrix is returned. So I'll jump down to main here. So I set my screen size to 1280 by 720 because that's the size needed for a thumbnail on a YouTube video. Then I set up the Pygame display. So you have the Pygame init there. Then set up the display and set the caption. And create the clock. So I define the corners for my complex plane rectangle. Then I calculate the pixel data. Then I load a palette. Then I apply the palette to the data returned from pixel data. And then turn that into a Pygame surface. So in the Pygame loop, this while loop goes until you click the X in the corner of the screen to close it. And this splits the image to the screen. And this is done 60 times a second. So once you hit the X, then it goes to quit. But I'll go back up here to the load palette. So the palette is just a file with an RGB values for each row, each line in the file. So appends that to the palette, and then I convert the palette into a numpy array. Here the supply palette is interesting. Got the NP, numpy max, goes through the whole matrix to find the maximum value. And then I create a scaling factor because I used the data, pixel data, to index into the palette. So you want the values to be in the same range as the number of entries in the palette. And then the pixel data is scaled. So this uses vectorization. So it does this multiply for every element in the matrix. And then, so here's where it generates the color data by indexing from the palette. And this is also vectorized. So it does the whole matrix with one line of code. So you can see with these print statements, the palette is 99 rows and 3 columns, so 99 RGB values. And then the pixel data is matrix 1280 by 720, so that's the size of the image to fit the screen. So then color data is a 3-dimensional array, so for every pixel now you have an RGB value. So if you're not familiar with vectorization, this here bit of code could be a little hard to understand. So normally you would write stuff like this with nested loops, which would take a long time to execute. So let's see what Cody has to say about it. So Cody uses Claude 3 Sonnet. So if you pay for Cody, then you can give him a brain transplant if you prefer him to have a different brain. But let's ask Cody about this piece of code. Paste didn't give me anything. There. So to ask Cody to explain this code including details of the vectorization. Ignore print statements. This is why I started using VS Code, because then I could use Cody. The apply palette function takes two arguments, pixel data and palette. Pixel data is a numpy array containing the values of the pixels, and palette is a numpy array containing color values for the palette. The function first finds the maximum value in pixel data using numpy max. This maximum value is used to calculate a scaling factor that will be applied to the pixel data values to map them to the range of indices in the palette array. Scaling factor is calculated. This ensures that the scaled values will range from 0 to the length of the palette minus 1, which are valid indices for the palette array. Next, the pixel data values are scaled using the scaling factor. The as type int is used to convert the scaled values to integers, as they will be used as indices for the palette array. The scaling operation is vectorized, meaning that it is applied to all elements of the pixel data array simultaneously, taking advantage of numpy's efficient array operations. So I don't know if it's just doing this with routine, using routine that was written in C, so compiled C code, or if it's also using the multi-core CPU or the GPU. So probably, I don't know if it'll default to using the more efficient methods, but there's probably a way to configure it to use your GPU. After scaling the pixel data values, the function uses the scaled values as indices to retrieve the corresponding color values from the palette array. Color data equals palette scaled pixel data. This operation is also vectorized as the indexing is applied to all elements of the scaled pixel data array at once. Finally, the color data array, which now contains the color values corresponding to the original pixel data values, is returned. The vectorization in this code allows for efficient processing of large arrays, as numpy can perform operations on entire arrays at once rather than looping over individual elements. This can significantly improve performance, especially for large data sets. So, run the program. So I'll have to do a video in the future about palettes that I just figured out yesterday how to create a palette and then use it from going 360 degrees around the color wheel. So you need RGB values to plot them, so you have to convert the color wheel into RGB values. Yeah, HSV is what I'm trying to think of. So I use all the hues on the color wheel and just use the maximum saturation and maximum value. So if you went all the way to 0 on the saturation, this would be grayscale. Then the value I think would make it how bright or dark it is. So I have full brightness and full saturation. So the Mandelbrot set is mapped to the values all the way around 360 degrees on the color wheel. So I've been thinking that I should be able to get more interesting Mandelbrot displays if I use just a portion of the color wheel. So previously I was doing this in C#, but I didn't know what to do with the colors, so that image I used in Python used this part of the Mandelbrot set. So in my C# version here, I have the zoom capability that I haven't got written yet in the Python version. So you can keep selecting regions to zoom in on. So then, if I click somewhere, it moves that to the center of the screen. And then if I'm lucky, that's a good value to use for generating the Julia set. So I use the center of the screen and create a Julia set. So I'll have to do the Julia set in Python yet. And then there's the zoom in, zoom out buttons. So on my C# code, I just used the hue calculated by the Mandelbrot algorithm. Subtract it from 255 to get to vary the green. And just assign it to the blue and set the red to 0. So it's playing around with this, trying to get different colors, but nothing much interesting comes up, but just playing with it this way. So, but now in Python I figured out how to use palettes to color this, so I can play with that more in the future. So that's all for this video. So hopefully I come up with some interesting experiments with palettes to make another video in the near future and add the zooming capability in my Python program. So that's all for now.